Welcome back, physics fans. Here we go, a 91 kilogram bicyclist. We're doing work quiz number 2, and these are my numbers, I guess. Accelerates from 5 meters per second to 10 meters per second without knowing or even calculating the distance traveled, which means you don't have the time, and you don't have the acceleration, so you can't use kinematics here. Determine the work done by the bicyclist to do this. So what's interesting is it sounds like a kinematics problem, but you can't do it at all without it because you only have initial and final. You don't have time, distance, so you can't do any of that. So here we go. How do you do that? And it says do not take into effect. So the kinetic energy final is 1/2 mv final squared, which is 1/2 times the mass, 91, times 10 meters per second, squared. So that's 1/2 times the mass times the velocity squared. Okay, and let's pull up Mr. Calculator. Turn it on. 0.5 times 91 times 10 squared is going to be 4,550. And the kinetic energy initial is 1/2 mass velocity initial, which is 1/2 91 and 5 squared, and that is going to be 1,191 times 5 squared, 1,137.5 joules. Okay, now that we have the initial kinetic energy and the final kinetic energy, work is defined as a change in energy. Whenever you do work, there's a change in energy, and of course they work. They went from an energy of 1100 to 4500. So that's going to be the kinetic energy final minus the kinetic energy initial. There's no potential here. There's no friction being lost or anything, so we don't do that. It's just these two numbers subtracted. So it's 3412.5. So that's how much work was done. Interesting. We were able to calculate work without using the formula force times distance, because we could not get the distance. And we don't know the force. So how could you do this? Couldn't do it that way. The next question. A 98 kilogram bicyclist accelerates from 6 to 8, and this time the bicyclist has to fight against friction by spending another 1,700 more joules of work. So the work is going to equal the change in energy, and the change in energy is going to equal the kinetic energy final minus the kinetic energy initial plus the amount of work done by the friction. Okay, and this will not be a negative 1,700, it'll be positive because that's how much work you had to put in there to overcome the 1,700 that took it away. Okay. So the kinetic energy final is equal to 1/2 mass velocity final squared, which is 1/2 98 times 8 squared. And that's going to be 0.5 times 98 times 64, 31, 36. And kinetic energy initial, uh, 17.5 times 98 times 6 squared. So the work is going to equal, actually I'll put it back up here, 3136 minus 1764 plus the 1700. And that's going to be equal to, take that, how much energy it ended with, minus how much it began with, and that's the change in kinetic energy, 1372, but friction took away 1700. So not only did he had to put 1700 in, he had to put also 1370. So we have to add those two together, because friction took away 1700. So it's 3072 joules is the answer. Boom. And here we go. Here's a nice conservation of energy formula. The stuff that we begin with, kinetic energy, potential energy, spring energy, heat energy, plus how much we add in, which is the work, is how much we're going to be left over with. Okay? Now, generally, I don't even remember ever seeing that you're starting off with heat energy, because heat energy never becomes efficient to ever change into kinetic energy or potential energy. Things go to heat. They don't use the heat to gain the energy. It's just thermodynamically not proper. So we have these. The beginning energies of these, how much you add in, becomes the finals. And this is how much heat energy we lose out of the system. Okay? Now, if you think about it also, that's a great formula. That's one to write down, boom, if you don't have it. But we could put all these initials over here and they'd become negative. So it'd be kinetic energy final minus kinetic energy initial. Well, final minus initial is just the change. So your work is going to equal the change in kinetic energy, positive, plus the change in potential energy, plus the change in spring energy, plus heat energy. There's the same formula in a different way. And if it's a conservative one where you're not putting any work into it, there won't be any friction, so this might disappear, and this work is zero. So as kinetic energy goes up, potential energy goes down, or vice versa. We're coming up with that right next lesson. Yay! Enjoy the little tune here. Thanks for watching. Subscribe. Remember, subscribe, like. Thanks.